Most of us treat soils as background, something we walk on, garden in, or wipe off our shoes and forget. But beneath your feet is a dynamic, living system where the majority of life on land exists. In fact, approximately 59%, up to 99%, of all species on the entire planet live in soil ecosystems. Even though soil biodiversity remains poorly understood and monitored, soil ecoacoustics is an emerging approach that listens to the underground vibrations produced by living organisms and physical processes. These vibrations, they can be crackles, pops and pulses, may tell us about the biological activity and condition of the soil without having to dig it up. Today we're asking simple questions. How do we listen to soil sounds, and what does it mean when soils become quiet? Stay tuned to find out more. Soil is alive and it moves. Healthy soils teem with life. Invertebrates such as earthworms and springtails and arthropods occur in astonishing numbers. Springtail abundance can range from 1,000 to 15,000 individuals per square metre, and earthworms from 20 to 300 per square metre, depending on the environment. And there are trillions of microorganisms. These organisms move through the pore spaces, feed, burrow, and interact with roots and microbes. Every one of these activities generates tiny physical disturbances. Now, soil ecoacoustics doesn't pretend to hear soil in the way we would hear sound in air. Rather, it detects vibration patterns moving through the soil, a dense, complex medium where mechanical waves carry information about biological and physical processes. Now, soil ecoacoustics doesn't capture distinct songs like birds in a forest. It captures activity, the presence of life and motion below ground. What soil vibrations might tell us? Above ground, ecological soundscapes studies have shown that diverse animal communities often produce richer, more complex acoustic environments, and researchers are now applying similar measures underground. Recent studies using soil ecoacoustics have found that sites with higher soil biodiversity and abundance of invertebrates show greater acoustic complexity and diversity of vibrational signals than degraded or less biodiverse soils. Now, this matters because traditionally soil monitoring has depended on digging, sieving and manual counts, methods that are time consuming and often destructive. Now, acoustics or vibrational monitoring offers an additional, minimally intrusive layer of information that can be collected repeatedly over time, offering a potential window into soil biodiversity dynamics and ecological change that might otherwise remain hidden. Why soil is a strange and revealing medium. Soils differ from air. They're not a simple acoustic medium. Instead, it's a heterogeneous, so a varied mix of solids, liquids and gases, mineral grains, organic matter, pore water and air pockets. So vibrations travel through this complex matrix differently from sound in air, with multiple pathways, reflections and damping effects. Now, this complexity is both a challenge and an opportunity. So the way vibrations move through soil is shaped by its physical structure, its moisture content and the activity of organisms within it. That means that vibrational recordings mix biological, physical and other environmental signals, offering a holistic signature of soil condition, not just a single variable. Disturbance leaves fingerprints underground. When soils are disturbed by compaction, tillage, pollution or loss of organic matter, etc., the patterns of vibrational activity can change. So emerging research, including work in restoration contexts, show that restored or mature soils often exhibit greater vibrational complexity than degraded soils, suggesting increased biological activity and community richness. This aligns with the well-established ecological understanding that soil biodiversity underpins key ecosystem functions, things like nutrient cycling, organic matter decomposition and soil aggregation, and is sensitive to land use and management. One promising idea is that shifts in vibrational activity might occur before visible changes above ground, offering a potential early indicator of soil degradation or recovery. That hypothesis is an active area of research. So is noise pollution effects. Human-generated vibrations enter soils from nearby roads, machinery or construction. These often low-frequency disturbances can travel through the ground and appear in ecoacoustic recordings, potentially masking biological signals or altering them. Because many soil organisms, from collembolans to earthworms, rely on mechanosensory cues, it is plausible that persistent human-made vibrations could influence the behaviour or activity. But the causal evidence is still developing and the mechanisms are not yet fully mapped. For now, we can say with confidence that human-made vibrations can enter soils, they can confound acoustic measurements, and it is a credible hypothesis that this noise could affect soil fauna and processes, a frontier that new research is now equipped to explore. How soil ecoacoustics data are recorded. Soil ecoacoustics typically uses contact sensors, things such as piezo microphones, geophones or accelerometers, buried or coupled to the soil. These sensors detect tiny vibrations rather than necessarily airborne sound waves, although if there are air pockets in the soil, some of these waves will be those pressure waves. Data are then processed, sometimes to filter out artifacts and summarize activity and analyze patterns across time and frequency. Now, increasingly, researchers apply machine learning to help distinguish likely biological activity, and while building validated libraries that link specific vibrational signatures to a particular organism is still a work in progress, the methodological foundations are there and evolving quickly. What it might mean when soils fall quiet. A sustained reduction in vibrational activity can be consistent with reduced soil organism activity or physical environments that limit mobility. For example, compacted or dry soils with reduced pore connectivity or fewer food resources. Quiet soil is not automatically degraded soil, but it does signal that something about the system's activity has likely changed. That signal can then prompt targeted investigations using other soil biological or chemical tools. So rather than interpreting silence necessarily as peace, we treat it as a cue for inquiry. What active soils tend to look like acoustically. So active, healthy living soils don't emit a constant signal. Instead, they show intermittent bursts and textured patterns across time, so pulses after rain, rhythms that might shift with daily cycles, and varied frequencies that suggest multiple processes at work. This complexity, measured statistically through indices of vibrational richness, has been linked with greater invertebrate presence and activity, which in turn is associated with healthier soil functions. This is why ecoacoustics holds promise. It adds a minimally destructive and continuous, but also potentially early indicator into the restoration and land management toolkit, complementing existing methods and potentially, in some cases, replacing them. Soil ecoacoustics is still young, but it's reshaping how we think about what happens below the ground. When we listen to soils, we're tuning into the rhythms of life itself. In a world where soils face mounting pressures from land use, climate extremes, and infrastructure, learning how to interpret these hidden signals may become one of the most useful tools we have for understanding and caring for the very foundations of terrestrial ecosystems. If you found this episode interesting or helpful, please don't forget to like and subscribe to the channel, and do me a huge favour and sign up to my free newsletter over at www.jakemrobinson.com. And remember, stay wild, inside and out.